Afternoon. How are y'all?
So?
Yeah. Okay. Not bad for Tuesday.
Yeah. At least it's not Monday.
Yeah, right. Just a reminder, we've got a week and a day from today. We have our exam. So next Thursday, the 17th. Huh?
May God have mercy on us.
Yeah, in theory, you're done with a lot of your homework, right?
Yeah.
Theory. So like if you've got a week before an exam, there's studies that say that if you study 2 hours a day, that's sufficient time to prepare for your exam, and you know that you could take a day or two off in between.
That's just studying, not the homework part, right?
Right. Well, like homework is studying, I guess, right? I guess it depends on how you look at it. So are there any questions on the homework? We're not completely through 3.9 yet.
I have a question for the final.
Okay.
Do we get a formula sheet for the final?
No formula sheets on the final, but you can have your own 3x5 note card.
It's a good thing my handwriting's super small.
Yeah, you could print it out if you want to. That's 3" by 5". Okay. Yeah.
Just a question about the exam. If we're in a situation where we have to take roots and turn it into like power, like raised to the half power, like I suck very badly at turning them back into. Would you be okay if I let them get it?
Yeah, that's fine. Yeah. So, question about the exam was turning the the fractional powers of x back into their respective roots. I don't have a preference on how you should write those. So if like if you take a derivative and you end up with like 3/2 x to the -3/2, I'm totally fine if you just leave it like that. Other people might write it as 3/2 times the square root of x cubed. That's fine too. I don't really have a preference.
The math labs makes you turn it back into the root form and it kills me.
Yeah, it's more, I guess, more proper, but I don't care. It's the same thing. Yeah.
Are we allowed to bring a microscope like super small? Like, next part of it?
No, just whatever your eyes can see.
All right.
Yeah.
No microdots.
Yeah, I don't know if you want to exam or do that.
Oh my god.
If you're talking about what I think you're talking about.
Microdots? Yeah. What are they used to? It was a spy tool.
A
They used to
Oh, okay, never
like
mind.
on the dot of an eye, it would print like all the codes it would need back in the 50s.
Oh, wow.
And then you just get like a little ocular device, and then you could read all the codes, so they would search letters.
I'm thinking about conscious altering.
Oh, that's microdosing. It's a little bit different.
Yeah.
That could be fun
Did
to
you have a
test.
question?
Hey, the numbers are red.
That's my mistake.
Well, there's even studies into like states of consciousness, like if you're studying inebriated, they suggest that you should take the exam inebriated.
Yeah. I don't know. I'm down to try.
Oh yeah, no. It was for me. It was just for me.
We'll have this class next semester.
I had to get more lead for my small pretentious pencil.
So, I mean,
All right, well, let's check this out.
How many pieces do you take off the pencil?
tired.
Like you just like disassemble it back up.
Oh, yeah.
Well, I also have to learn small lead. It's just one more step than that.
Sure.
Okay, so homework 3.8, number 7, use implicit differentiation to find the derivative of cosine y sine x equals 4y. So the derivative of both sides of our equation, the derivative of cosine y would be what?
It's sine
Times y prime. Yeah.
right, because it's y.
So the derivative of the outer function, leaving the inner alone, times the derivative of the inner. Remember, it's with respect to x plus the derivative of sine of x equals the derivative of 4y. What's the derivative of 4y? 4 times y prime. 4 times, so you got a constant times f of x, right? Okay, and then in order to find the derivative, we've got to solve for y prime. So it doesn't matter, we just want the y primes on one side and everything else on the other. It really doesn't matter. Other than this, like if someone puts it on the left versus the right, you'll just have a difference of signs. So what side do we want the y primes on? What do you prefer?
Gets rid of that.
The right? Yeah, so we can get rid of that negative. So we'll have cosine x equals to 4 y prime plus sine y. Okay. Just so we know we're taking the sine of y, and it's all multiplied by y prime. And then we factor out what we're solving for. We factor out a y prime, so we can divide through by what's left over. So we have 4 plus sine y. All of that times y prime. And then y prime is cosine over that stuff. So cosine of x over 4 plus sine y is our y prime. So if you're writing your y's as a function of x, that's fine. Some people do that just so they can see the chain rule a little bit easier. And also, just as a reminder, in 3.8, if you look through any of the MyMathLab help, they're going to be, instead of y prime, they're going to use dy over dx. And then they're solving for dy over dx. So that's the notation that they default to. So again, whatever notation you're using, I would just be consistent with it. Don't try to switch it up. Does anyone have any questions on that example? Okay, any other homework questions?
I will read 3.7. Number 19.
I just have a question for that one that we just did. Can we rearrange it in the beginning before we find the derivatives and stuff? Like, can we just move cosine y over to the other side and then sine x? So
Yeah.
at the end, it won't change anything.
It won't change anything. Yeah, you can rearrange the original equation before you find the derivative if you wanted to. Yeah, that way all of your y's are on one side. Okay, so calculate the derivative of the following function with respect to p. So our independent variable here is p. When we have p plus pi squared times sine of p to the sixth, we're going to use what rule? The product rule. Yeah, because it's a product of two functions of p. So y prime or dy over dp, y prime, we've got the first times the derivative of the second plus the second times the derivative of the first. So 3.7 was the new rule we saw in 3.7 was the chain rule. But then it's like we introduced the chain rule. It's like, hey, here's a chain rule with a product rule. Here's a chain rule with a quotient rule, etc. So that's what we're dealing with here. We've got to use the chain rule to find these derivatives that show up in our product rule. Chain rule there and the chain rule here. So there's the product rule. They calculate these derivatives individually here off to the side. What's the derivative of sine of p to the sixth?
6 sine.
So we've got to take the inner function and leave it alone. So the derivative of sine, leaving p to the sixth alone.
The inner function is p to the sixth.
Right.
Correct?
The inner
Okay.
function is p to the sixth. It's the sine of p to the sixth. So the derivative of sine, cosine, times the derivative of the inner. So that derivative is 6p to the fifth times the cosine of p to the sixth. Okay. Any questions on that? And then we have to compute the derivative with respect to p of p plus pi squared. Okay. So again, another chain rule. The derivative of the outer using the power rule, leaving the inside function alone. Oops. P plus pi to the first times the derivative of the inner function, which is just p plus pi. What is the derivative of p plus pi with respect to p?
Just one.
Just 1? Do you all agree? So we just have 2 times p plus pi. Okay. So those are our derivatives we've got to put back into the original problem. So maybe we have enough room to write it here. Derivative of sine of p to the sixth. That derivative. Okay, so we're done with the derivative because we don't have other derivatives showing up. I'm pretty sure my math lab would take that as an answer. There's a common factor of 2 times p plus pi that we could factor out, but that's the gist of the derivative there. Anybody have any questions on that? So try to stay as organized as you possibly can. The mistakes, a lot of the times the mistakes I see on the exam is because people aren't organized and they're kind of referencing the wrong thing. You know, they've got all their work, but when it comes time to, you know, state what the final answer is, they're looking at the wrong line in their work because it's just sort of all over the place. So try to stay organized. I think that'll help out a lot. All right, any other questions on the homework? 23, same section. So find the what? What does that notation mean?
Second derivative.
Second derivative.
Right.
Find the second derivative. For e to the power x, 8 times x squared. So first derivative, y prime, would be what? E to the 8x squared?
Times 16.
Yeah, times
16x.
the derivative of 8x squared. Remember, the derivative of e to a power is just e to the power times the derivative of the power. So there's e to that power times the derivative of the power, which is 16x times e to the 8x squared. Okay, first derivative. Second derivative, we've got to take the derivative of the first derivative. So how are we going to take the derivative of 16x e to the x squared?
Product rule?
That's a product of two functions of x. So we have the first times the derivative of the second plus the second times the derivative of the first. Okay, for this one, we've already done that. That was our first derivative. So we know that this is just going to be, again, 16x e to the 8x squared from our first step. And then we still have this 16x here times that. Plus e to the 8x squared times derivative of 16x times 16. So that's y double prime. Sort of clean that up a little bit, but that's the second derivative. What is 16 squared? 256. of 256x squared e to the 8x squared plus 16 e to the 8x squared. So that's probably okay. And just for the record, I don't consider multiplying constants and stuff like x squared. I don't really consider that simplifying. That's, once we start like factoring things out and dividing common factors, like that's simplifying. Here we're just combining like terms, which should be a practice that you are doing already. Just because it's a cleaner than the original, and having a bunch of things multiplied together. Carry out that multiplication. Naturally, if it's like 16x plus e to the 8x squared, all of that to the third power, naturally you would just leave stuff like that. But sort of the more like trivial types of multiplication, you probably should be doing. Okay. Anybody have any questions on that? Well, any other homework questions then? And we left off then in 3.9 with the sort of like the final derivative we get in this section. That was the generic exponential function. So we said the generic exponential function, we're going to call it b. Remember, b is just some number that's not that's greater than 0 and not 1. So the derivative of b to the f of x is b to the f of x times the ln b times f prime of x. So when we went through this derivation of how we got that derivative here in blue, that was just giving us a sense of how do you take the derivative of the generic exponential function or the exponential function being the outer function itself. So this here in purple is a more generalized version of that includes the chain rule. So we'll look at a few examples. Specific examples. We did verify that the formula here in blue or purple does work for the function e to the x. So the e to the x is just the base b equal to e. And so we did show that it worked for that one. Let's find the derivative of y equals 4 to the negative x. And honestly, the biggest issue that I see on exams taking the derivative of exponentials is people want to take the derivative of exponentials like they're a power of x. So this will never work for when our variable is an exponent. You never say that it's that using the power rule, because you're not dealing with a power on x. So this is for a power. I don't know if you want to look at it like this, or like x to the b power. That's when we would move the power down and subtract 1 from it. Is everyone clear on that? The difference between an exponential function and a power function. Okay. So the formula says that we take the derivative of our b to the x, or this is now b to the f of x rather. by saying it's 4 to the negative x times the natural log of the base, 4, times the derivative of the power. So exponentials always have themselves showing up in the derivative, right? When we took the derivative of e to any power, we said it's e to the same power times the derivative of the power. So that's another way, I guess, to know that you're taking the derivative of an exponential correctly, is it should have the same function in the derivative. Okay, and then the derivative of our negative x is negative 1. So we have 4 to the negative x times the natural log of 4 times negative 1. So there's b to the b to the f of x times the ln of b times the derivative of f of x, just directly from our formula. So you might see this written as negative 4 to the negative x times ln 4.
Can the ln be negative? Would it be correct to use negative ln?
Yeah, you could write that. You could write the negative in front of the ln. So you could write it like that.
So it doesn't matter which one it is?
No, it doesn't matter. You know, whatever's clear to you that this thing here is actually negative 1 times 4 to the negative x. Right? It's not the same thing to say that that's negative 4 to the negative x. Well, in the way that we might think about that if we put that negative out front, I think there sometimes is a tendency to think about it as negative 4 to the negative x, but that's not the same thing that we have here. We have a negative 1 times that exponential. The base of that exponential is positive 4, and that negative 1 does not affect the base. Any other questions about that? So, I mean, in theory, it's not anything difficult. It's just yet another derivative rule you have to remember. I don't know how many we have up to this point, but there's a lot. All right, let's see what we have next. Nothing. So, example 2 and example 3. I want y'all to work on these. So example 2, y equals to 250 times 1.045 to the x. And example 3, y equals to the natural log of 10 to the power of x.
I would treat it as a constant. 2 weeks ago. Yeah.
This is an affection. It's so much pressure. Besides pressure right now.
need a product rule? No.
Well, yeah, it shows you have your 250 weeks. Flows like that will take advantage of it. I'm wondering, because this all becomes 0 to go long. So I'm wondering if, because I times.
So what do you give you?
That's what I got. Mine's all that backwards because I took the derivative of this and got rid of it. But it comes to the same.
Yeah, you could.
Yeah, that would be the.
Yeah. But did you get the same answer? That's really what I'm concerned with.
Yes.
Can I see it?
Well, the 250 is our.
Oh, no.
Yes.
So we've only gone over 2, right? We haven't gone over 3. As far as like these.
Yes.
Okay. Okay, I'm just making sure.
No, I was just saying this is part of handling that. But you still have to have your derivative.
That your prime? Yes. 1 prime equals 250.
Hey, do you not understand? Because I do not know. So your B is just like this.
Okay.
And then this is and so.
I have some in my office. Would you rather have that than abrasive
And
towel?
then following this, I started with, it's just the same thing.
I'm sorry. Derivative of the outside.
1.045. And then ln
Yeah.
of
1 over 10.
So how did you just literally pulled your constant out? Yeah, I pulled the 250. You can do it as either
and then
product
the
or
derivative
or you can do it
of,
either as greater or
so that one's
either
just
way.
for after that.
Mike did it as a product. I did it.
And it zeroes out.
Okay. Yeah, because the derivative of the constant goes to 0. That whole tail end.
Oh, yeah, you're right, yeah.
It winds up looking exactly the same. So it's 1 over. Wait. No. No. Wait. No, yeah.
So it's not just me that just turns different things just to see if
It's simply just 1 over 10 of the x.
You guys said that real quick.
I cheated it.
Natural, is it the natural log?
Oh, wait, can you do the chain roll? Yep.
It is.
Yeah.
It is.
There's a chain roll on this, right?
Yes.
I thought I was doing good until I just heard you say that.
What?
Talking about this.
Oh, yes, I'm sorry, my bad. Yeah, we're talking about number 3. Yeah.
Cool. So, what was your simplified answer for this one?
So basically, you just put brackets around your 1.045.
So yeah, this 250 will still be all the time. Like this.
So, but you didn't simplify
start out like that.
No. For number 2? No. We just leave it all ugly like that.
Oh, I see what you did.
Because
Yeah, because if you can find, yeah. I was like, how did you get
yeah.
that?
Yeah.
But I'm confused on everything.
All right.
So it is a chain rule.
It is, in fact, a chain rule. So it's derivative of the outside with respect to the inside. So it's the derivative of natural log, so it's 1 over 10x, times the derivative of the inside, which is 10 to the x over 10. And then you just multiply those together to get this fraction. So it's 10 to the x. 10 to the x is cancelled. Just L is that. So it makes sense.
Yeah, that makes sense.
What L is.
The natural log.
So,
Log base E.
do you know the, so you got the exponential function, this is the mirror image of it.
Like, what does LN stand for though? Is it like log natural?
Yeah, so it's the, if you have the growth function here, then
So that would just be there.
so the further out it goes, the more simple it becomes.
It was like written as something else before LN. Was it log of x? It was log base E of x. That's what I was trying to remember. I was trying to remember what it was before just LN.
It's been a year and a half since I've actually done the
Yeah.
word log.
Yeah.
So,
This is the
It's not just a whole lot.
all I know is it was created because sailors could add and subtract, but they couldn't do derivatives. And it made it really easy for them to figure out how fast, how long their trip was going to take at a specific speed.
Is that really hard?
Yeah, it's why, I don't know why, but it is why.
Because they had
So the B is the
Chemistry, our teacher just tells us that it's so that it's easier.
Oh, it's super easy. It makes it way easier. Super easy.
Because it puts
Then
everything on a
speaking
linear
English.
graph as opposed to a function.
Yeah.
You shouldn't do it. Just see if something's right. Oh wait, that was
Why
right.
would you do that as a product? That's so much of it.
I was like,
All right, so the derivative of 250 1.045 to the x is 250 times natural log of the base 1.045 times 1.045 to the x.
so this,
Yeah.
Can you treat that as a constant? The 250 is a constant as well?
Yeah.
Okay.
Yeah, that's kind of how we thought of it here when we had it just constant times our derivative.
Okay, cool.
Yeah.
I did it the same way without doing the product rule.
Okay. Yeah, you wouldn't do a product rule here because it's not the product of two functions of x.
Oh,
Can you parenthesize before the natural log and after the final exponent of x? So you have 250 times parenthesized natural log of 1.045 times 1.045 power of x.
Like just the whole thing in natural log in parentheses?
Because I essentially just, use the product rule. You have the left-hand side, the right-hand side zeroes out because you're using the derivative of 250. So you're then left with 250 times the derivative of 1.045 to the power of x.
Yeah.
And then once I found the derivative, which is essentially that natural log, et cetera, I kept that parenthesized.
Okay.
That entire piece.
First
right
piece
there.
right here.
So
Like
it'd
this
be like put your first parentheses just before the ln. Perfect, and then after the final exponent.
Oh, I see.
You know what I mean? The whole thing.
Like this?
Yes.
Yeah, I think that's totally fine, as long as you realize it's the ln of that number
Right.
times that exponential. Like
Right,
that,
'cause
that
I
exponential doesn't go with this
I wrote the
1.045.
exponent first, so that
Okay.
way the exponent is separated by the natural log.
Yeah, that's fine.
You know what I mean?
Yeah.
I just flipped the numbers.
The order, yeah, because we just have three things multiplying each other here.
Right.
You know, it doesn't matter the order. That's A times B times C.
Right.
So you could have C times B times A, or, yeah. Yeah. So just be careful with these exponential functions. They're not going to combine with other things. Unless you had another identical exponential function, 1.045 to some other power, generally you're not going to combine these things with other stuff that come up in their derivatives. Okay. Any other questions on that example 2? And the derivative of ln of 10x. Remember, there's a couple of ways to look at these. Once we start dealing with logarithms, the properties of logarithms are always there, whether you want to use them or not. So I think it's easier to say that before I take the derivative, I'm going to simplify y by the property of logarithms that says if I have the log of something raised to a power, the power can come out front to multiply the logarithm. So before I take the derivative, I'm going to use properties of logarithms to rewrite y as x ln 10. And then I just have the derivative of x times a constant. So like the derivative of 3x is 3. The derivative of negative 12x is negative 12. So the derivative of natural log 10 times x is just natural log 10. No, don't feel dumb. As long as you got that, there's other ways to get there.
Well, I mean, you got the right answer the first time, but you did it a totally different way.
Yeah, so I mean, I think maybe the default, we're just used to seeing that we've got an ln, so we do 1 over the function times the derivative of the function. Right, and there's nothing wrong with that. So you have 1 over 10x, and the derivative of 10x is 10 to the x rather, times the ln of 10. And then these cancel out.
In that,
I'm just confused because on my notes, what the previous uses in general, the derivative of e to the fx is the fx times ln times f prime x.
Yeah, so if you wanted to see that f prime here, then we're just taking the derivative of the power, which is just 1.
when you did the notes for that first section, maybe I totally missed it, but I thought you wrote it as the derivative of ln x is equal to 1 over x, not 1 over x times the derivative of x.
Right, yeah, so that's the derivative of, so if we're taking just the derivative of the natural log, there's really not I mean, I guess there is a chain rule here, but we just said that was 1 over x.
Right.
Right. Really, what we're not seeing here is that the fact that the derivative of the argument is sitting here, but that again is 1. So we just get 1 over x anyways.
Where are you getting the 10x, the ln 10x?
This one here,
Yeah.
that one that's the derivative of 10 to the x. So like all of this right here is the derivative of 10 to the x.
Oh, okay.
The 1 over 10 to the x came from the natural log, is 1 over. So the derivative of the natural log is 1 over the function times the derivative of the function.
Okay. Oh, it clicked. Okay, got it.
Okay. Yeah, and we just didn't write that specifically when we had the derivative of ln of x. We could have very well said the derivative of ln of x is 1 over x, 1 over the argument times the derivative of x, times the derivative of the argument. We just didn't write it that way. The more specific version, we did say the derivative of the natural log of any function was the derivative of that function over the function itself. So, yeah. So ln of 10 is the derivative of that. Any other questions on example 3? Sure.
So in this case, we're considering x to be 10 to the x.
Yeah, the argument is 10 to the x. So we have 1 over 10 to the x times the derivative.
Are we going to be talking about just log in general, or are we going to always use natural log?
Yeah, we'll look at the generic logarithm next. So our third derivative that we're looking at here is the general logarithm. What's the general of, or what's the derivative of like the log base 2 of x or the log base 5? It's the, well, that was an example. I'm going off of 1, 2, and 3 here. These 1, 2s, and 3s. Not to be confused with example numbers. Okay, so the way we want to think about this, again, we could use the definition of the derivative. We haven't done that thus far with the other ones. Similar to when we took the derivative of the natural log, how we derived that. If y is the log base b of x, then by definition of the logarithm, it's the same thing as saying b to the y is equal to x. We don't know the derivative for log base b of x, but if we look at it as b to the y equals x, then we can do implicit differentiation. So what's the derivative of b to the y with respect to x? As y is a function of x.
B to the y, ln b y.
Oh, you're right.
Yeah, so we have b to the power times the natural log of the base times the derivative of the power. Right? Yeah, equals to the derivative of x, which is 1. And then we solve for y prime. Y prime is 1 over b to the y times ln b. But what's b to the y? X, right, so then we'll write b to the y as x. Y prime is 1 over x times the natural log of b. And this is the derivative of this here. So the idea of implicit differentiation is also useful when we look in the next section, when we start taking the derivative of inverse trig functions. They're all derived or proved using implicit differentiation. So again, this is sort of limiting because we're not seeing the chain rule applied to this. This is just telling us how to take the derivative of a function when the outer function is the log base b, like the log base 2, log base 5, whatever. So the more general one would then be to look at what's the derivative of the log base b of some function of x. Whether it's x, whether it's negative x, whether it's sine x, whatever it is. So hopefully we've seen enough of these. We've got the derivative of the outside, so it's 1 over the argument times the natural log of b. So 1 over f of x times ln b. Then the chain rule says multiply by the derivative of the inner function. Yeah, so depending on how you write this, or we could just say it's f prime over f of x times ln b. Whichever one of those makes more sense. But it's almost the how we looked at the derivative of the natural log. We said it's f prime over f when the outer function is the natural log. When it's any other logarithm, it's f prime over f times 1 over ln of b. So that's the generic one we want to remember. Let's just look at, does this work? For y equals to the natural log of x, which is, of course, yeah, the same thing as the log base e of x. We just don't write it that way, right? So even though it seems like we have 4 different derivatives for logarithms and exponentials rather, you really only have 2. You have what is the derivative of b to the x, and what is the derivative of the log base b of x, because both of those, when b is equal to e, you have the other 2 common ones, e to the x and the natural log. So it says, in order to take the derivative of this logarithm, we take 1 over the argument times the natural log of the base. And then we multiply all of that by the derivative of the argument. So that's in line with what we have here with this piece right there. The derivative of x is 1, and on the bottom here, ln of e is also 1. So that's verified that it works for the natural log as well. So if you just want to remember those 2, then remember those 2 because they account for all logarithms and all exponentials. Anybody have any questions about that?
How does the natural log get to the bottom of the function and not on the top instead?
So like here, you mean?
Well,
Like why is this one
Or
here?
down there, when we do the y prime, like how does the natural log end up at the bottom of the function?
Just
the definition.
Yeah, that's just how you have to take the
Oh,
derivative.
okay.
Yeah,
Okay.
that's just how you have to take the derivative of a logarithm. And so seeing that the definition is you have to take the derivative of the logarithm this way, it's one of the reasons that we go through the derivation or the proof of why the derivative is what it is. Because otherwise it's kind of weird. You've got these natural logs of whatever floating around and the derivative. We can see from our work there in blue exactly where that comes from and why it has to be there. Maybe, I don't know. Okay, any other questions about this? So a couple of examples. On the derivative of y equals the log base 2 of 3x. So using the derivative rule, it says that the derivative of a logarithm is 1 over the argument times the natural log of the base. So 1 over 3x times the natural log of the base, which is 2. Times the derivative of the argument times the derivative of 3x. So we have the derivative of 3x is 3 over what we had originally, 3x ln 2. And we can cancel the 3's. 1 over x ln 2. So the only difference with a general logarithm versus the natural log is the multiplier of ln of the base on the bottom. That's the only addition we have. Does everyone see that? Like if this were the natural log of 3x, we would say it's 1 over 3x times the derivative of 3x. So the generic logarithm just has this multiplier in the denominator. Sorry.
Do you have like a centralized like sheet with the logarithms or something on or not the logarithms, the theorems and like?
Just like all the derivative rules?
Yeah.
I don't think I have a condensed version of the derivative rules. I can see if I can find one. If nothing else, I can take the snippets from your notes and just kind of put them in there.
Yeah.
Okay.
That'd be really rad.
Really rad? Wouldn't be tubular.
No one
Sorry,
says two.
I was playing Super Mario World.
Oh.
Y'all remember that? If you beat like Star Road, then you play those other levels. It was like cool, awesome, tubular.
Oh, yeah.
Yeah.
I know all of what
Yeah.
you're talking about. I know the whole game.
Awesome. Yeah, my son was like, "Why are they named that?" I'm like, "I don't know. I think it's the Japanese trying to connect to our culture." I really didn't know. But so tubular, I'll put that. I'll try to compile that. Yeah, so they might not be expressed as like a chain rule.
Yeah.
They'll be expressed more like what we have here in blue. That's just generally how they're presented. Okay. So, all right. Well, again, it's a logarithm. There's 2 more ways we can look at computing the derivative of this function. So we'll just say maybe this is part 1a. Part B, we could say we started off with the log base 2 of 3x. Remember I asked you to look over properties of logarithms. Maybe you did, maybe you didn't. How can we rewrite the log base 2 of 3x according to properties of logarithms? What? Okay, so save that thought. We'll do that next.
Log base 2 3x over log base 2 2? Or is it the
That's
log
the
base?
that's a legitimate formula, but it's the change of base formula. Like you're thinking, I think you're thinking of the change of base. If we wanted to change that to like the log base e, we could change the base. So maybe there's 4 ways to look at this. Do y'all remember the change of base formula? Opened a can of worms. So I mean, like, it is worth mentioning because there's multiple ways to think about these things. You know, the reason I think it's beneficial to have multiple ways to think of this is so you just don't get stuck in thinking of it one way, right? If you forget how to do it like how we normally do it in class, you can fall back on some algebraic technique, maybe.
Isn't it,
that can
are you
help
thinking like the log base 2 times 3? But you separate the 3 and the x
Yeah.
into 2 separate log base 2's.
Yes, by a certain operation, yeah. So the log base b of we'll just say this is m, whatever that is. Is the log base a of m divided by the log base a of b. That's the change of base. So we could say I don't like the log base 2, right? I want to change that to a log or a log base e, natural log. So I could just change the base and say it's the natural log of 3x over the natural log of 2. And then I could say right before I take the derivative, I'm going to look at it as y equals to this constant, 1 over ln 2 times the function of x, ln of 3x. But here again, you have another rule if you wanted to utilize that. But the idea is, okay, we can change the base. What's the derivative of the natural log of 3x? What is it? Sorry. Derivative of the natural log, because 1 over ln 2 is just a constant, right? 1 over x, yeah. It's 1 over 3x times 3. So that derivative is just 1 over x. So notice y prime is 1 over x times the natural log of 2, which is what we had here. 1 over x times the natural log of 2. So I'll just put a check mark because it's the same thing. So change of base. The other one is using properties of logarithms. Remember, if you have the log of a product, you can separate that as the sum of the logarithms. So another option, before we take the derivative of the log base 2 of 3x, is to rewrite this as the log base 2 of 3 plus the log base 2 of x. Properties of logarithms, then take the derivative of our function. So what would the derivative of the log base 2 of 3 equal? 1? Anybody think anything different?
0.
0?
Yeah.
So with respect to x, what is the log base 2 of 3? Is it a function? No, it's a constant. So the derivative of the log base 2, just type it in on your calculator. It's just going to give you some number. The derivative of the log base 2 of 3 is 0. What's the derivative of the log base 2 of x? So we go back up to our formula here in blue. Derivative of the log base 2 of x is just 1 over x times the natural log of 2. Again, same exact result. And then the final way to look at this, y equals the log base 2 of 3x, was how, Esri? What did you say?
Isn't it log, no, sorry, 2 to the y equals 3.
Right, yeah, it's to first convert the logarithm into an exponential. 2 to the y equals 3x. So this was exactly how we derived the formula for that. If you're going to do it this way, then you have to remember to do implicit differentiation. And we've already done that with the more generic one, so we know how that works. But yet again, it's another way to take the derivative. So the derivative of 2 to the y, as y is a function of x, is 2 to the y ln 2 times y prime. The derivative of 3x is 3. So solving for y prime, we have 3 over 2 to the y ln 2. We know that 2 to the y is actually equal to 3 to the x, or 3 times x rather, sorry. 3's cancel out, 1 over x ln 2.
You're just showing us there's a bajillion ways to think about this.
Yeah, there's multiple ways to think about it.
So you're getting a different answer though, then, right? If you were to, use like the first and the second rule.
Which one? That we did in part A?
I guess really any of them.
Well, all of them gave us 1 over xln2, right? Whichever method we used, we got 1 over xln2. So yeah, like the in-between might look different, but the final result is 1 over xln2. The in-between's different because there were like 4 different ways to think about the log base 2 of 3x. Is that kind of what you're looking at?
I don't really know. As of right now, I'm not like.
Okay.
A couple more drinks in will be okay.
Yeah.
I was thinking, we're just like changing things, because that sounds fun.
Yeah, and again, not to confuse you with multiple ways, but maybe one of those resonates with you more than the other one does. They're all valid, so it doesn't matter which one you use.
Let's see which one resonates with me.
I'm gonna do one more before we take a break. Let's see how long.
Oh, I
this
thought you meant
takes.
like another way to do the same problem. And I was like, all right, let's go.
Never eat, bring it.
Okay, how about the function log base 4 of tangent x?
Why you gotta eat?
Okay, so we've got a chain rule. It's the log base 4 of another function. So we take the derivative by saying it's 1 over the argument, 1 over tangent, times the natural log of the base. So we have 1 over tangent times ln4 times the derivative of the argument. So times the derivative of tangent. What was the derivative of tangent?
Secant squared.
Secant squared. So the derivative then is secant squared over natural log 4 times tangent. Maybe we could simplify that, but that's the main idea.
It's too much work.
So 1 over the argument ln base times the derivative of the argument. That's how we take the derivative of any logarithm. Yeah.
How would you simplify it? Would you simplify it by crossing out the secant x squared with the tan x, right?
Maybe, I don't know. We could write secant as 1 over cosine because tangent is sine over cosine.
And then you cancel out the cosines and left with sine.
Yeah. Then you could cancel out 1 over the cosine, but then you might have like a sine over cosine on top. So, but yeah,
Let's not. Let's just
do that. Any other questions about the logarithms? So again, you just have to spend time with these. Otherwise, we've got like 20 derivative rules. It seems like they kind of start to bleed into one another if you're not continually working with them. All right. If there aren't any questions, we'll take a break.
Group of friends they happen to have at that point in time. And the first one of them.
Okay. I'm gonna start a new page because we're gonna talk about somewhat of a new function, but. Before we actually look at that here, let's go back to one of those properties of exponentials. Property number 2, property number 1 rather. If you have, no, what am I thinking of? I guess all of them are useful, but specifically for what we're going to look at, property number 3. Sorry. Property number 3, see how it allows us to write an exponential b to the x as e to the x times the ln of b. So when we look at probably functions that are new to us at this point, but if we look at a function like x to the x, more generally, we want to sort of talk about what if y is equal to a function of x to another function of x power. So there's something that's not quite exponential, something that's not quite a power function either. So we want to talk about those functions, and you know, maybe you've seen this function here. For example, 1 plus 1 over x to the x. Has anyone seen that, or does that look familiar?
Yes.
So if you've seen that, sometimes even algebra textbooks will define the number e as part of this function. They'll say the limit as x approaches infinity on 1 plus 1 over x to the x. So these types of functions, in this context anyways, show up as a definition for the function or the number e. So there are real life problems where this shows up. Virtually anytime you deal with e, you're dealing with this thing right here. So these functions do show up. We got to talk about how do we take the derivative, because they're not exponential. We can't just use the exponential rule to take the derivative, and they're not powers, so we can't use the power rule to take the derivative. So the way, now anyways, we'll talk about another differentiation technique in a minute, but for now, to take the derivative of this function, we use property number 3 on page 1 and rewrite x to the x as e to the natural log of x to the x. Which, according to the properties of logarithms, the power at least, the natural log of x to the x, we can rewrite that as x times the natural log of x. We'll just say, so y is equal to e to the x ln x is the same thing as x to the x. So let's just verify that visually. So just to verify that those are the same, over here for positive values and 0, x to the x and e to the x ln x are the same function. So when we think about the functions that aren't exponential nor powers as e to the x ln of x, then we can take the derivative of that, because to take the derivative of x to the x rewritten in this way just entails us taking the derivative of e to this power, right? So that's a crucial observation, to take the derivative of this. Y prime is the derivative of e to any power is e to the power times the derivative of the power. Since that's the same as x to the x, we're going to find the derivative of that, and that will be the derivative of x to the x. So we'll here compute the derivative of x ln x using the product rule. First times the derivative of the second plus the second times the derivative of the first. And what we get is just 1 plus ln x as the derivative of x ln x. Times e to the x ln x power. So that is the derivative of x to the x. But we also know that e to the x ln x power, that was the same thing. We just algebraically rewrote x to the x as this thing. So in place of e to the x ln x, we're just going to put our x to the x. So that is the derivative of x to the x. So the idea of using that property number 3 comes back out in 4.7 when we start looking at limits. Because when we look at limits of like a function to another function power, that's sort of when we can start to justify that the definition of the number e is actually that limit. But we've got to wait until 4.7 to look at that again. Right now, we're not computing limits on that. We're just taking the derivative of that. So to sort of put this in a more general setting, for now anyways, one way to take the derivative of y equals to f of x to the power of g of x. One way to take the derivative of this is to rewrite y as e to the g of x times the natural log of f of x. And take the derivative of e to that power. See that. Hopefully we've seen e to a power's derivative enough times to where we're pretty comfortable with that. And so these things can get sort of elaborate, but other examples are like sine of x to the x squared power. You know, any kind of functions of that form. One plus 5 over x to the 2x, and so on and so on. We'll look at a technique that will give us a second way to take the derivative of these types of functions, f of x to the g of x. But this is one way to do so, And I think this way of looking at functions f of x to the g of x is a little bit more conducive to when we start computing limits on those types of functions. Because to compute limits on those types of functions, for certain values, we always have to rewrite them as this blue piece right here. So knowing that property 3 and you know, keeping it fresh or working with it when you can, I think is going to help out a lot once you get to section 4.7. Even though we're about to look at another way to take the derivative of that. Okay. So any questions on this? All right, then, well, the other technique of integration relies heavily upon properties of logarithms. So the technique is called logarithmic differentiation. So, you know, really, I guess the question now is why do we need another technique to take a derivative when we have the derivatives rules for all of these different types of functions? I think we can motivate it with not a generic thing, but with a specific example. So just consider a function y that's, I don't know, let's say it's x cubed minus 2x squared plus 1 all to the 5th times the square root of, I don't know, 3x minus 1. And all of that would be over, let's say, sine to the 4th of x cubed, let's say. So it's not that we couldn't take the derivative of that, of y as it is with methods we already have, right? We have the quotient rule involved for that derivative. Then we have a product rule involved, and then we have a chain rule involved, right? So you've got 3 derivatives involved in taking that single derivative of y. So there's nothing wrong with what we have. It's really tedious to take the derivative of a function that consists of multiple types of derivative rules. And so what logarithmic differentiation does for us, through the properties of logarithms, if you're familiar with those, we can take products and turn those into sums. We can take quotients and turn those into differences. And we can take powers and just turn those into multiplication. So we'll say y another technique to find y prime. There's too many rules. Product, chain, and quotient rule. Properties of logarithms. Allow us to rewrite products as sums, quotients as differences. And powers as multiplication. So it's probably worthwhile just to write those properties that we're going to utilize out. So the log of a product, as we saw earlier, that turns into the sum of the logarithms. So you might say, well, like if we're going to use these properties in that function that we considered, there aren't any logarithms, right? But it's up to us to introduce the logarithms. So you have to introduce a logarithm to perform logarithmic differentiation. So that's the product, the quotient, the log of a quotient is the difference of the logarithms. And we've sort of been working with the power property. Log base b of m to a power. Power comes out front to multiply the logarithm. So all three of those are utilized. It just really depends on what your function has as far as the operations. But those are the properties you should be familiar with. We'll write down the process and look at how it unfolds. Here's the process. So the first step is to take the log of both sides of your equation, of your function. So take the log of both sides. You can use any logarithm you want because they all have the same properties, but typically in practice we use the natural log. So we'll take the natural log of both sides. The second step is to, before you take the derivative, to simplify using properties of logarithms. So we introduce a logarithm, simplify using the properties of logarithms, then we take the derivative. Of both sides. And so from here, we just recall that the derivative of the natural log of y will be y prime over y. That's the derivative of the natural log of f of x is f prime of x over f of x. So that's sort of the implicit differentiation coming up again. So we take the derivative of both sides, And the final step is to solve for y prime or dy dx. Or f prime, whatever notation you're using. So how do you know when to use this technique? It either will say, or it's totally up to you. Like if the instructions say specifically use logarithmic differentiation, then you're going to want to use this. In any other setting, the derivative rules we have for like standard functions, sine, cosine, x squared, all of that stuff is a lot more efficient to just take the derivative as we know. But logarithmic differentiation also works. So we'll start off with something we already know. So use logarithmic differentiation to find y prime. So let's just say we had the function sine x. We know the derivative efficiently is cosine, but let's just see how this process works. Step one, we have to introduce the log to both sides of our function. So we're going to take the natural log of y and the natural log of sine of x. So take the log, then you simplify using properties of logarithms. We can't simplify the log of y or the log of sine. So it's already simplified. Then we take the derivative of both sides. Like we mentioned, the derivative of the natural log of y is y prime over y. What's the derivative of the natural log of sine of x? 1 over sine x times the derivative of sine. So 1 over sine times cosine. Is everybody all right with where we're at? Just a couple of chain rule on the right-hand side, implicit on the left. Okay, and then the final step is to solve for y prime. Which means that we have to multiply through by y. So we would say y prime is cosine over sine times y.
So on an exam, is it possible that you might ask us to solve a problem using like logarithms?
Yeah. So there's more than likely will be one question at least on logarithmic differentiation. So we would explicitly say use logarithmic differentiation to find the derivative. Yeah. And just remember that y we started off with as sine of x. So y prime is really cosine over sine times sine. That was our original function.
So you just say cotangent x times sine x?
Yeah, if you want to, but then you would have to simplify that to see that the derivative is actually cosine.
Oh, I see what you're saying.
We already knew that, right? We already knew the derivative of sine was cosine. We're just showing that this process also works. You know, there's a little, there starts to become this like technical aspect because sine is sometimes positive and sometimes negative. And then when you take the log of both sides, the log always has to be positive. You know, so there are these technical things that we really don't worry about per se. This is again just illustrating that the process does work.
This is still doing
Okay. Any questions on that? I think let's just look at one more of these where it really doesn't make sense to use logarithmic differentiation, but just to solidify that it does work.
Can you do a simplified fraction? Like, or a
A fraction?
a non-overkill fraction?
Yeah. So how about we'll look at
Or maybe you can put like two numerators that, or
like the x plus 1 over x minus 1.
yeah, something that maybe we need to use. We need to consider, a couple rules, kind of like the
Okay.
first one.
Yeah.
Like the one you wrote for us to consider, but that one obviously is a little intense.
Yeah,
So, like,
we can look at one of those
something that kind
similar
of
to
follows
that.
the same.
Yeah, we'll look at one similar to that in a
same
minute.
guide.
So we'll get a little bit more into it. So I don't know, let's look at like x cubed, for instance. The derivative of x cubed, we can easily verify the process of logarithmic differentiation. We introduce the logarithm on both sides. And then before we take the derivative, you're going to simplify anything you can according to properties of logarithms. That's the whole point of introducing the logarithm. So I see people will do logarithmic differentiation and they won't use any properties of logarithms. And you're not doing yourself a favor when you do that, because the derivative of something that's complicated is just as complicated if you introduce a logarithm and don't simplify it first. So
like moving the exponent.
yeah, so here all we could do, the ln of y is still the ln of y, but we could say the natural log of x cubed is really just 3 times the natural log of x. So there's our simplified version according to the properties of logarithms. And then we'll take the derivative of both sides. So y prime over y on the left. What's the derivative of 3 ln x? It's just 3 over x. And then we'll multiply through by y to solve for y prime. But y was x cubed, right? So it's 3 over x times y, which is 3 over x times x cubed, which is 3x squared. From here to here? Here to here?
I feel like I might have done an extra step somewhere. Oh, yeah, I just written an extra line. I just
Oh, right,
read
all
the
right.
derivatives in before I did them.
Okay.
That's all I did.
So, all right, just maybe start off with a couple of ones where we can easily verify that it does work. Anybody have any questions on this? Okay, so let's then go back to the, well, not the one we wrote down earlier, but something that's comparable to that. So something like x cubed minus 2x squared plus 1 to the fifth, all to the fifth, times the square root of 3x minus 1, all over, let's do x squared plus 4 to the 8th. So again, we could take, you use the quotient rule, the product rule, and the chain rule to find the derivative. But we're going to use logarithmic to do this. So the first step, we take the natural log of both sides. And so at this point, you don't want to start taking the derivative because you can simplify the expression on the right and simplify it fully with properties of logarithms. Don't just use like one and then start taking the derivative. You can do that, but again, you're not really doing yourself any favors. So we're going to simplify this expression on the right fully with properties of logarithms. So we've got the natural log of the quotient. So we can rewrite that as the natural log of the numerator minus the natural log of the denominator. Oops.
Is changing the ln(y) to the y prime over y, is that something that can be considered during simplification, or can doing it, I guess, essentially too early mess up the answer or mess up the equation?
It just depends on how you handle it, but technically, if we were to say that at this point y prime over y is equal to that,
Right.
that's not true. Because
No, it's not.
because we have the derivative of one side of the function equals to the function that was present originally. So you're saying that the derivative is still equal to the function.
I gotcha. Okay.
So we would want to simplify completely in terms of properties of logarithms before we take the derivative of any side. Okay, so we have the ln of y equals this here. Is everybody all right with what we've done? That was property number 2, the log of a quotient. So then we see we still have this first term. It's the log now of a product. And the second term is the log of something raised to a power. So this last term here we can write as minus 8 ln of x squared plus 4. There isn't a property for the log of a sum or a difference. So the log of x squared plus 4 just has to stay as is. We can't simplify that. But the first term here, we can separate that according to the first property of logarithms. So it's the log of the first factor plus the log of the second factor. Again, we could take the derivative at this point, but it's still, you still have some complicated derivative formulas involved.
I think you forgot to put the 1 in there.
Oh, yeah. Now we have the first term, we can use the power. The second term, ln of the root 3x minus 1, can we do anything with that? Yeah, we want to consider the square root again as the 1/2 power. So we have 5 times the natural log of x cubed minus 2x squared plus 1. So there's really no more like complicated chain rule. I mean, it kind of is with the natural log, but at least you don't have 2 chain rules. Plus the 1/2 power comes out front to multiply the log of 3x minus 1. And then this one was already simplified. So basically, you know you're done when you don't have like the log of products, quotients, or powers. We just have the log of the sums and differences of things. So we know that we're done fully simplifying that. And again, we haven't taken the derivative yet, so this is still the log of y. Okay, so then we take the derivative of both sides. So y prime over y, derivative of the left, equals to 5 is our constant. What's the derivative of the natural log of x cubed minus 2x squared plus 1?
2x minus 4x over that.
Over that? Yeah. So let's do that. Let's do that off to the side, just so we're not rushing through this. The derivative of the natural log of x cubed minus 2x squared plus 1. So we have 1 over the argument times the derivative of the argument.
You're using product rule for this, right?
That's a chain rule.
Or I mean, essentially, you're finding that derivative because you're using a product rule. Is that why? Like, are you
No.
seeing 5 as your, 5 times the derivative of natural log plus natural log of 5 times ln, etc.? Is that
I suppose you could.
really essentially why you're getting the derivative?
Yeah, so really it's just a constant times that log function. So the 5 just comes out to multiply the derivative of the logarithm.
I mean, like, why are you even, I guess, why would instinctively, what would, make you, I guess, even attempt or even find a purpose or a reason for getting the derivative of that natural log expression to even begin with?
Because we've got the ln of our function is all of this stuff.
Right.
But that's just a different way to look at our function. We still need to take the derivative of our function. So from this step to this step, we have y prime over y because we took the derivative of the left. So we have to take the derivative of the right. We're taking the derivative of this equation, essentially, or of this function.
The whole thing?
The whole thing, yeah. So here's the derivative of the left. To find the derivative of the right entails we find the derivative of the log here, the log of 3x minus 1, and the log of x squared plus 4.
So I guess then if you have to find the derivative of the whole thing, and maybe you'll get to it, but are you not considering the derivative of essentially the coefficients, 5, the 1/2, and 8?
No, because with properties of logarithms, we were able to just turn those into constants. So like the power of 5 is now just a constant times that function of x. The square root is just that 1/2 constant times that function of x, and so is the 8. Okay. So yeah, that derivative here then, 3x squared minus 4x all over this. take the derivative of the log of 3x minus 1. Down here too, derivative natural log 3x minus 1. So again, you've got 1 over the argument 3x minus 1, 1 over 3x minus 1, times the derivative of 3x minus 1. So 3 over 3x minus 1. That's the derivative of the natural log of 3x minus 1. Or minus 8 times the derivative of the natural log of x squared plus 4. Oops, sorry, you did right. I'll do that down here too. Derivative of ln x squared plus 4, 1 over x squared plus 4 times the derivative of x squared plus 4, which is 2x. With 2x over x squared plus 4. So that's the derivative of the right-hand side. Derivative of the left-hand side, again, was just y prime over y. So if you do this right, at most you should just have a chain rule involved with the logarithms. So no quotient rules, no product rules. We got rid of a couple of chain rules. And then we solve for y prime. We're just going to multiply through by the original function. And I don't expect you to multiply this stuff out. So we have y prime was the y times all of this stuff here. We have oops. I'm just rewriting the function y here. So there's y times all this stuff. So it's not pretty, but neither was the original function. So I mean, you could reconcile these constants if you wanted to write this as 15x squared minus 20x on top. If you wanted to say that this is 3 over 6x minus 2, or negative 16x over x squared plus 4. That's really all I would expect for you to clean that up. Multiplying all of this stuff out, you definitely do not have to do that. So that's our derivative.
That's it.
That's it. I don't know if that was sarcastic.
Can we see this on a graph,
Lay it
please?
up.
Yeah, you want to graph it?
Punch the entire thing into decimals.
Yeah.
The next 20 minutes of what you do.
No, because it's multiplied by like the constants.
Yeah, which one?
Like the or x cubed minus 2x squared plus 1. And then essentially the root of 3x minus 1 because it's basically a 1 over. 3x minus 1?
Yeah.
You get this cancel out? Or is it because
It-
it's multiplied by a constant?
Yeah, well, I mean, if you were to take this stuff in blue and multiply it by all three of these, then you might could cancel that root with this right here. Is that what you're focusing in on?
And the first rest.
Yeah, and so this would cancel with this, right? And you would have this root, this power over this thing. Yeah, so like each individual piece would cancel to some extent if we multiplied it through, but not fully, so. So anyhow, whether you think that's an easier process than just doing the product quotient chain rule all with the same function, I don't know. Maybe you can try that using the product chain and quotient rule to see what that looks like. But we need to be familiar with this process. Okay. So are there any other questions on this? Maybe you're still trying to catch up or don't know what to ask. So just make sure you look over those and know what's going on. Because I think if you look at this and know what's going on, I mean, it's a lot simpler of a process, really. Even though it doesn't look like it.
Is my math lab gonna have any of those intense ones?
I don't think theirs are too bad. They have, I mean, yeah, they have some complicated ones, but they're. So before y'all go, so we're going to go back to the next class. We're going to start looking at how to use logarithmic differentiation to take the derivatives of these types of functions. So we already mentioned one way to do so. Then we're going to look at some of these functions with logarithmic differentiation as well. Okay? So that's what we're going to do next time.
Are those functions called something? They're not still exponential?
Yeah, they're not, but they're not called exponential. I don't know that they have a particular name.
That's what I thought.